Is starting, has started. Let me double check it is actually recording, then we'll go ahead. All right, it is actually recording. And we'll log into Moodle. And get started. Yeah, the quiz won't start until 9:15, which is when the file becomes visible to all of us here. So we can start with the homework assignment because the quiz and the homework assignment, they're all related to what we are currently talking about, which is how to use, how to access parameters and local variables, and they're all on the stack in the frame basically. So are there any questions about that? No questions? There's only one thing I have to remind you guys about the homework assignment. Do not use EBX. If you use EBX, you have to save and restore it because EBX is one of the very few registers where the caller expects it to be unchanged. So the EBX, EBP, those are the two registers that should be preserved from the perspective of the caller. Okay? But ECX, yes, it's okay. EDX is okay. EAX is okay. The stack pointer should still be balanced because if it's not balanced, you should not be able to return back to the caller because you won't be looking at the return address by the time you execute the return statement or the return instruction. So that's basically just a whole bunch of little things that you need to pay attention to. I saw quite a few people turning in find max n already, so that's pretty good. That's encouraging. So for those of you who turned in find max n already, was it difficult, easy, kind of, just about the right difficulty?
Just about right.
Just about right? Anyone else? Nope. Okay. All right. So we are pretty much done with topic 9 at this point. We talked about parameters and local variables and the return value. And there are two links here because one is a new one and one is the older one. They talk about the same type of content. This one is the newer one, and this one is the older one. Because the older one is basically a link into what I call, a book, but it's really just, some of my writing, and they're kind of strung together. The new one is a kind of more independent module, which is by itself, but they talk about the same thing. So I would encourage you to, if you only have time to read one, read the new one. Okay? If you have time to read both, it's not going to hurt. Are there any questions regarding parameters, local variables, and the return value? And at this point, we have only talked about return values that are scalar, which means they can be contained in EAX as a single register. In C and C++, you can actually return a structure. Even in C, you can actually return a structure by using the return statement. And obviously, in that case, we cannot use a register because a register only has 32 bits. And how big a structure can be, how big of a structure can you create is arbitrary, right? You can make structures that are really, really big. So we're going to skip over that topic for now because I think I have something that's a little bit more interesting or more useful to talk about. If we have time, we can come back and talk about this one, how to return a structure. It has to do with the stack as well, and also a implicit pointer that is passed as a parameter. But we won't talk about that, at least for now. So what we will talk about, this is going to release at 9:15, so I'm just going to look at my watch occasionally. Yep.
I have a question. Last time we talked about the order of the parameters on the stack before we stored the return address.
Correct.
But I don't have anything in my notes about the order of local variables once we get into the...
That is somewhat arbitrary.
Okay.
It's up to the compiler to decide. And what I found is the compiler does not always follow the order of the definition of the local variables. Apparently, if you have arrays, it will define the arrays first, so that the arrays will have a lower address, and then all the individual variables will have a higher address. I have no idea why that is the case, but that's what I'm observing, which is kind of interesting.
Okay, thank you.
Sure. And this is also partially why in C and C++, when you declare a local variable that is an array, the size of the array or the number of elements in the array must be determined by compile time. It cannot be runtime determined. because if it's runtime determined, then you cannot really pre-calculate the displacement or offset into various items on the stack anymore. Because the space for arrays is actually statically allocated on the call frame. But the call frame is constructed on the fly in an invocation, but the displacement is predetermined at compile time. And that's why when you want to use a local variable in C and C++ that is an array, the number of elements has to be determined by compile time. It cannot be determined at runtime. Whereas in other programming languages, you can do it either way. You can say, okay, now we get into this scope, I want an array with this many items, and it will be created on the fly. And that's only because in Java and many other languages, arrays are not allocated on the stack. They are actually allocated on the fly from the heap. And then we don't have the restriction of a certain size in that case. All right. Any other questions? No questions? All right. We have 7 more minutes to get to the quiz. If you have been working on FindMax, and I think you'll be okay with the quiz. Okay, the quiz is just showing you the C code on one side, showing you the assembly code on the other side, and you don't have to debug anything. The assembly code is known to work. Okay, what you are going to do is to identify what is this register doing here, what is this operand doing here. So you have to identify parts of a program that is already working. So you're not going to debug it. You just have to identify parts. So that should not be taking too much time.
What do you mean by what is it doing? What value does it have? Or?
Right. What is the role of this register? Or
how
what
does
value
it relate
does it
to
have?
the C code?
And how it relates to the C code.
So like a sentence.
Yeah, something like that.
Okay.
Yeah, just give me a little phrase to say, okay, I think this is that in the C code.
The value's here and it's this.
Right.
Blah, blah, blah.
Yep. All right, so what we'll do now is we're going to move on to topic 10. And topic 10 talks about structures. And we're going to do structures in assembly language programming, which is kind of strange, but it is necessary. Okay, this is something that is actually useful in certain types of programming. So before we talk about, I can click on the slides and actually tell you what it is, but instead of doing that, I can give you, sample programs as well. So what I'll do is I'll give you a sample program in C first, and then we'll look at the assembly version of the same program and go like, okay, but how do we do it in assembly? Because there are some challenges that we have to overcome in order to access structures in assembly language. All right, so we'll go to, I'll just create this folder called struct here, and we'll basically just look at one particular program using structures, and it is in C. As a, it's supposed to be quiet now. Let me make sure that it's turned off. Yep, it's Walmart telling me that it's out of stock again. But it's supposed to be off, because Tasker. Oh, okay, I forgot to turn on that profile. Because last Thursday was a Thanksgiving, and I didn't want the phone to silence itself. Okay, now it's silenced. I apologize for that. Has anyone taken Bob Irvine's classes, like Visual Basic? No? Okay, he's really kind of strict on cell phones, and I think one time his own cell phone went off, and he had to give the whole class points for that. Because he'd actually take points off if someone's phone rang in the class. He would actually walk over to the student and ask for the student's name, and then he would mark it on his roll sheet. Anyway, you guys are not getting 3 points because of that, because I never take 3 points away from you anyway. All right, so let's go ahead and take a look at a program using a structure. Okay, a structure is basically the same thing as a class in C++, except it is an original feature in C. So I have a structure called X, and the semicolon is actually necessary in C. In the class definition, you don't need a semicolon after the definition of the class, but with a structure in C, you do. So we'll go ahead and just say, inside a struct X, we have an integer I. We have an array of, we call it the buffer of 32 bytes, and then we can have a single char called ch here. Okay, so I have no idea what this structure is going to be useful for, but this is really just a cookie cutter. Okay, in other words, it is almost the same thing as a class in C++, except all members are by default public in a C structure. So the way I use this inside a function is, not going to be very, challenging, right? I mean, if I just give you a main program here with a local variable that is a struct x, let's call it var1 because it's not really for a particular purpose. Then I can access individual members like var1.I is initialized to, let's say 33, and then var1.ch is initialized to the ASCII code of the question mark or something along that line. Okay. So does this remind you of what you have learned in cisp310 about structures? Okay. Nothing really out of the ordinary here. Okay. And then the other thing we can also do with structures is we can take the address of a structure and then use a pointer to access members of a structure. So if I have a pointer here that points to a structure of type X, then I can say PTR gets the address of var1. Then at this point I can say PTR points to a particular member, let's say buffer. And since buffer is an array of characters, then I can say, okay, let's go to the 6th element because it starts the indexing from 0. So this is actually talking about the 6th element in the array. And we can just say, okay, we want to make it a lowercase a character. Okay, so that's also something that you should have learned in cisp310 is how to use a pointer to a structure and access individual members using that pointer. Are there any questions about this code? No questions? Okay. So what we'll do today, after the quiz, is to be able to write code to resemble something like this, but in assembly language. Now, there actually is a good reason why we want to do something like that. Certain things you do in multi-threading and some other types of programming, the code can only be written in assembly, but the caller is going to be calling from C and C++. So that means, in C and C++, you'll be dealing with structures, but in the assembly code, you have to understand how a structure is actually created and be able to access individual members of the structure in assembly language. So now the question is, how can we get that across? Because the definition of a structure, which is from line 1 to line 6 in this particular program, is a C syntax. Okay, the assembler does not understand a structure definition. So the question now is, okay, so how can a program written in assembly be able to access the individual parts of a structure? And if I change the structure definition itself, I want the assembly code to update as well, so that it is always up to date and be able to locate the correct member, at the correct offset. Okay, so that's the objective. And it is 9:15 right now, so we'll go ahead and do the little quiz here. The quiz is actually in the form of 2 source files, so now that it's open, people can actually download it. It's just a tar file or tar.gz file, and I will use a text editor to show you the content, and this way you can work on it, just looking at the screen. I thought about printing it out, but I thought, since there are only 5 blanks that you have to fill in, this should be okay as well. So this is 2014, 12.2. So what I'll do is I'm going to display the code side by side. Fibonacci.c is the source code in C, and then Fibonacci.uppercase S is the assembly code. And I ran the program already, so I know this code actually works. The C code and the assembly code are equivalent. And let me maximize. Okay, so your job is to, not quite displaying everything. Let me change the font size a little bit so that we can see everything. So let's go to appearance, change it to 13, just make it a little bit smaller so that we can see the whole, or at least enough of the program that of the parts that you need to answer. And I don't know how to shift this bar over, but what I can do is to make this wider. Is it helping? Okay. All right. So this is the C code in to implement Fibonacci. How many people kind of know about the Fibonacci series of numbers or values from like maybe a previous class? Okay, so this is not really difficult. It's kind of like a factorial. It is used a lot to demonstrate how to do recursion, except this one has a double recursion, because if you look at line 11 and line 12 in C code, it is a double recursion, which means it has to find out what is the Fibonacci number or value of n minus 1, and then you have to add the Fibonacci number of n minus 2, add it together, and that becomes the actual return value of this particular invocation. Okay, whereas factorial only needs one recursion. This one needs two. So the question is, I just want you to answer these questions. On line 8 of the assembly code, what is this operand? What is it really referring to, corresponding to a construct in the C code? That's what I'm asking. This is another one. Okay, what is -4 in parentheses EBP actually referring to? What is the equivalence in the C code? That's what I'm asking. And I don't want you to answer me, because I want this to be an individual answer. Yep.
So if you want the value, like the variable that's pointed to?
Yeah. What is it equivalent to in the C code? So you have to answer that particular question. On the other hand, when you look at line 18 of the assembly code, here's another question. What is in ECX here? Okay, and this one, you can also answer this question relating it to the C code. Okay, because that's one thing you can actually do here. And then we also have the same thing here. Okay, you can specify the value too. Okay, if you want to specify the value of ECX and how it is the equivalence of ECX, the value in the C code, you can also do that. So there are 6 spots where you have to fill in the blanks. Line 23 is asking what is the purpose of this instruction. So that one has no equivalence in C, because in C you don't have to do this. This is something that you only have to do when you write when you write program in assembly code. So you have to kind of answer the question without referring to the C code, because it's not explicit in the C code. And the last part is this one here. What is in EAX at this point? So that's asking after the pop L instruction, what is in EAX at that point? And that one kind of relates to the C code. You can kind of refer to certain constructs in the C code as well. So that's your question. 6 spots, 6 spots to fill in. And I'll give you guys maybe 10 minutes or something like that to answer the question. Yep.
So, what do you mean in ECX? There's no parameter that's going. Like, what do you want to know?
You mean here?
Yeah.
This one?
Yeah.
The value in ECX after the pop L instruction has a special meaning. So, and you can find that you can find the equivalence in the C code. So you need to kind of make that link and say, okay, after the pop L instruction, ECX has the value of a certain expression in the C code. just gonna wait until the pens and pencils are down, and then I'll go ahead and collect the answers. Just kind of putting the fork and the knife, on the plate.
So I can filibuster?
It's always one of those, man. Maybe 2 more minutes, and I'll go ahead and collect it. Oh, make sure you write down your name on the piece of paper, so this way I can score and put it onto Moodle. Otherwise, I'll create an anonymous student account. One more minute. Okay, 30 seconds. All right. So I'll go ahead and collect the answers, and then we'll talk about this. So this quiz, is kind of designed to make sure that you understand the concept that you need to understand for the homework assignment. So hopefully, by starting on the homework assignments early, you guys can Thank you. All right. So let's go ahead and take a look at the C code. With this particular program, the assembly code actually very closely resembles the C code. I'm not doing any trick or there's a little bit of shortcut around, line 18 to line 24 or so. But the way I use the stack and the call frame is consistent with how it should be done in C and C++. Okay. So the first thing we want to do is to look at the C code and find out how things are getting allocated. So I'm going to use commenting here to basically document how the stack is being used. What is as far as the subroutine Fibonacci is concerned, what is the first thing that we put onto the stack, which means it has the highest address?
Parameter.
The parameter, okay, which is n, right? So n is pushed on the stack first, and then what is the next item that is pushed on the stack?
Return address.
The return address, which is done by the call instruction, and this is done by the caller. So the return address is the next thing on the stack, and because all of the items on the stack are 4 bytes long, so I don't even bother to use 4 spaces. I just say that each line is representing 4 bytes. What else is put on the stack? Now that we're in the subroutine, we look into the assembly code. So what is on the stack right now?
UEP.
Old EBP, okay? The OBP that belongs to the caller is now saved on the stack so that we can restore that later on. And then what else is now on the stack after that? Exactly. R, the space is reserved for R using the subtract instruction on line 6 of the assembly code, but I didn't really quite put a specific value there because I don't know, what R should be on line 6 of the assembly code. So all I did is to subtract 4 from the stack pointer to basically say, okay, these 4 bytes are now reserved. Do not touch it. Okay, I'll use it later. Okay, now the big question is, where is ESP pointing to? Out of these 4 items on the stack, EBP points to which one? Old EBP. That's right. Okay, so EBP points to its own value that was saved earlier before we changed EBP. Okay, so if that is what EBP points to, we can also say that this location is 0 bytes away from where EBP points to. Is that okay? So this is called the based addressing mode, where you use a register to and also a displacement, or you can call it an offset to specify the actual address. So this is basically at the location of 0 plus EBP. This one would now be at 4 EBP because it is 4 bytes above where EBP points to, and this one is going to be 8 EBP because it is 8 bytes above what EBP points to, and this one, being a local variable, is actually -4 EBP because it is 4 bytes below where EBP points to. Is that part okay? Because this is really important, because once you understand this part here, then you can answer the questions on line 8 as well as line 11. And then after that, the other questions will kind of follow. Okay, so knowing this is how we utilize the stack in the C code, let's find out how we can answer the questions in the assembly portion. So on line 8, I'm asking what is 8 EBP, and you can tell from the C code here, it is actually just parameter n. So if you just say n, that's fine, okay? Or you can say parameter n or the parameter, because there's only one of them. So any one of those answers will be considered a 100% correct answer, okay? If you just tell me it is 8 bytes above where EBP points to, that would not be an acceptable answer, because that's what the operand actually spells out. But I want to know what it is corresponding to in the C code. So this one is just R because it is 4 bytes below where EBP points to, and according to our calculation, that's exactly where the local variable R is located. All right, so this one is a little bit kind of it takes a little bit more time to process this one. So basically what you need to do is to start on line 14, because line 14 is overwriting EAX with basically n in this case. So EAX, okay, if I just document it line by line, this is how it goes. If I document this line by line, EAX is n at this point. It is local variable, a parameter n at this point, because we know 8 EBP is n. And we are now subtracting 1 from EAX, which means EAX is actually n minus 1 at this point. Now you don't have to do all of this stuff here because it's just steps that will lead to the answer. Push EAX does not change the value of EAX at all, so I'm not going to do anything. There's nothing that I need to specify here. You can basically we're pushing n minus 1 on the stack. The value corresponding to n minus 1 is now pushed on the stack. And why are we pushing that on the stack?
It's a parameter for the recursive call to Fibonacci.
Yep, it is a recursive, it is the parameter to the first recursive invocation of Fibonacci. It's corresponding to the call on line 11, okay? So assuming the subroutine doesn't mess up the stack at all, don't you think, when I do the pop out instruction on line 18, I'll be popping the same value back? So the value that we are popping back is what? N minus 1, that's right. Yep, go ahead.
Because we consider EAX the return value, and that ends up being R, could we infer that by popping EAX, we're popping R, which is also equal to N minus 1?
No, not really.
Okay.
Not really, because in this case, I'm asking what is in ECX, not in EAX. Now, EAX does have the return value of the Fibonacci number of n minus 1, but I'm not using it right now. I'm just looking at the stack and say, okay, whatever I pushed before the call, I just want to pop that back. Now, normally we don't do that because normally the parameter is useless, after the call to the subroutine. But in this case, it does. It is actually useful. Okay. All right. So if ECX has the value of n minus 1 at this point, the next instruction doesn't change it, right? The next instruction doesn't mess around with ECX at all. It's just pushing EAX on the stack. So what exactly is EAX at that point? If I want to document what we are actually pushing on the stack, EAX is Fibonacci of n minus 1. Because EAX is the return value of a subroutine. And I kind of talked about that right before the quiz. Remember, I talked about, when the return value is a scalar, if it fits into EAX, EAX is used to return a value. So that actually kind of, help you, with this particular question a little bit here. Okay, so, but line 819 of the assembly code does not change ECX in any way, but this one does, okay? On line 20, we are subtracting 1 from ECX. ECX exactly. So on line 18, ECX has the value of n minus 1. If we subtract 1 more from it, what is it? It becomes n minus 2. Or if you specify the long way, that's fine as well. Okay, because it was n minus 1 before, now we subtract 1 more from it, it becomes n minus 2. Is that okay? Now, if you just kind of look at the context of how ECX is used on line 21, you can kind of guess what it is, because we are calling Fibonacci on line 22 again, right? So the two recursive calls, one is on line 17 and the other one is on line 22. Each one requires the parameter to be pushed prior to the call. And from the C code, we know the value that we need to push on the stack is n minus 1 for one and n minus 2 for the other one. So you can kind of guesstimate, you have a 50-50% chance by just randomly saying one is n minus 2 and the other one is n minus 1. That will give you a 50-50% chance of guessing the right one. But if you just do the analysis on the first one, it is n minus 1, so this one has to be n minus 2. Yep.
So saying the first one corresponds to the first call of Fibonacci and the...
That would be fine too.
Oh, good.
Yep. Well, you have to say you're pushing, it's the parameter of the first call. Okay? Because that's what it is.
There's a lot of eraser on there, so maybe some of it's...
Okay, I'll put it under the microscope and look for erase,
we'll send it over to the science department.
The NAS. NSA, sorry, NSA.
They know me.
They know you. You're on file. Huh?
Yeah.
You're in their cache. Yeah.
On the
frequently accessed item. Okay, so if we know that ECX, what we're pushing on the stack is n minus 2, then line 23 is really just deallocating the space that we have used for n minus 2. So what is the purpose? And remember, I said about this. What I said about this instruction, it has no equivalence in the C code, because in the C code there's no explicit way of doing that because the C compiler does it already. So what exactly is the purpose of line 23? Yep. If you just say to deallocate the parameter or balance the stack, any one of those phrases or terms would be fine. Okay, so we just balance the stack, deallocate the parameter. They're both considered 100% correct. All right. So once we balance the stack, what is on line 24? Now, line 24. It's a little bit tricky, okay, so there are several possible answers that I can take here as well. On line 24, we move EAX into -4 EBP. From the C code, we already analyzed that -4 EBP is our local variable R. So on line 24, we are putting a particular value, EAX, into R. So on line 25, we are popping we're popping something into EAX as well. So what is on the stack at that point? So you have to look at the sequence of the push and the pop instructions and also the stack balancing instructions. What are we exactly popping into EAX? Okay, let's check it out. Okay, starting on line 16. Okay, line 16 pushes n-1 on the stack. On line 18, that is now popped from the stack, so the stack is now balanced again. The next instruction pushes EAX on the stack. So what we are pushing on the stack is now the Fibonacci of n-1 that is now pushed on the stack. And then we have a second push on the stack, which is n-2 on the stack. After that, we do the call, and then after we come back, we get rid of the n-2 on the stack. And then we get to this pop instruction here. So what are we actually popping into EAX? Which push corresponds to this pop?
EAX is line 19 this one.
Yep, the push on line 19 is corresponding to this one. So EAX now contains the result of the Fibonacci number of n-1. Yeah, this one is a little bit tricky because it require you to kind of track down the sequence of push and pop instructions in order to find out, at this point, what is actually in EAX at that point. Okay. Now, obviously, with this one, there will be partial credit. Okay, because most people, I'm hoping, can get the first two questions, N and R. The identification of one is the parameter and the other one is the local variable R. I think that should be okay. The third one, which is n-1, I'm hoping most people can get that one too. On line, I think it's on line 15, not line 15. It's on line 18. So there will be partial credit. That it's not going to be all or none. And that's why I put all the questions along the way, because it prompts you to think about, okay, what is 8 EBP, what is negative 4 EBP, so at least some people will be getting some partial credit. Any questions about this one? And do you know what I'm training you guys to become?
Programmers.
Hackers. Because this is what hackers actually do. What they do is they take the executable of a program, they load it into memory as if they're ready to run it. There's an equivalence of GDB in Windows that can load an executable into Windows or any operating system. And then this is what they do. They disassemble the code in assembly, and then they look at the source code to figure out how something is actually done. So why would someone want to do something like that when you're not in a class, your grade doesn't depend on it, and it's actually your job? So why would your employer want you to do something like this?
So you can find little holes that you can inject extra code into, or
Exactly. Yep. This is what people who crack code do. They need to look into how a particular program does things. For instance, I'll give you one really good example. This is how people find, zero-day exploits, or one of the ways people find zero-day exploits. Do you know what is a zero-day exploit?
something that's brand new, nobody's found this vulnerability and patched it yet.
Exactly. So, and how is it used? How would one use a zero-day exploit?
Usually to take over
To take over?
whatever operating system computer.
Usually, yeah, exactly. They can compromise an operating system, like Stuxnet. Okay, Stuxnet, I think by itself has 3 zero-day exploits, which is unheard of, prior to Stuxnet. Most programs, most viruses only have one. Okay, as soon as people find one zero-day exploit, they just deploy it. It's like, okay, let's try to get as much as we can, using this particular zero-day exploit. Stuxnet, as far as if I remember correctly, had 3 zero-day exploits, which means somebody found 3 previously unreported security holes and kind of weighed up and saved all of that and put it into one single virus. And the single virus, Stuxnet, is not supposed to cripple a PC or to turn the PC into a bot, in a botnet. What is the purpose of Stuxnet?
To cripple nuclear
refining, machinery in a very concealed way as well. Okay, it's not going to cause a meltdown or anything that would cause blaring alarms. It's supposed to accelerate the centrifuge in a way that will wear out the centrifuge, much quicker than it is supposed to. So it's a really kind of interesting thing, but this type of thinking is what can lead to the construction of virus and countermeasures of viruses as well. Okay, so I'm thinking that I'm hoping that this will become useful to at least some of you who will be getting into computer security and doing countermeasure of viruses and infections to operating systems and programs. I don't know. What do you think? Tech is teaching people how to hack and crack programs. This is a bad thing. Is it a bad thing?
No.
Because if I don't do this, would other countries be doing the same thing? Absolutely. Some of the hackers are country, state funded by an entire country. And I'm not talking about a country like Norway with only several millions of people. We're talking about countries with more than 1 billion people, and that kind of narrows it down right away to 2 countries, right? Yeah, they're subsidized. They're basically state-run hacker schools. Yep. All right. So we'll go ahead and get out of this program. But I do want to show you the C code corresponding to the call of Fibonacci. It's just regular C code, okay? Nothing special, and the program works. Okay. In other words, I can call Fibonacci from C code in main.c, and it works exactly the same way as the C version of the code. Okay. Any questions about all this stuff? No. Okay. So if there are no questions about this, I'm hoping also for people who have not started or have not finished the homework assignment, find max n, will find this particular quiz a little bit helpful for the homework assignment itself. So, if you have done the homework assignment and you take the quiz and okay, I got all of this down already, then it's good. Okay. If you have not gotten started with the homework assignment, the quiz will help you with the homework assignment. So either way, I'm hoping it will be helpful in some way. All right, so with this out of the way, I'm going to go back to my structure program. And, oops, I think I have one window open on it already, which is right here. All right, so we'll go ahead and write the same code, but in assembly this time, okay? So let's find out, how we can do something like that. Now, structures are strange because how many bytes is in a struct X anyway? I mean, it's what do you think? Let's make it a little bit more fun. Okay, let's change this a little bit and make it slightly more fun. Let's make it 27 bytes here. Okay, well, I don't really know. So something that I do not know, I'm gonna use GDB to help me understand how a structure is organized. Okay. There's no rule in the C standard that says that buffer has to follow I or CH has to follow buffer immediately. Okay, so there can be gaps, and the compiler can feel free to rearrange the arrangement of the members inside the structure. Okay, so I really don't know. Okay, so let's go ahead and compile this program, run it in GDB, and then we can find out the displacement to individual members of a structure. So that's what we'll do next. gcc-c-o struct.c. Oh, I just did something really dumb. Oh, it's still here. Because normally if I do something like that, it will destroy the source code, but it's actually smart enough not to do that. Okay, so now we can debug struct, which doesn't really do anything particularly useful or interesting, but I'm going to run it anyway. Because what I want to do is to print out var first. Okay, print var1, and you can see that, oh, there's a whole bunch of gibberish, but that's okay because I have not initialized the structure yet. So, where the structure is located in memory, there's a whole bunch of bytes that are uninitialized at this point. So it is okay to see all kinds of gibberish at this point. But this is not even what I'm interested in. What I'm really interested in is the address of each individual member. That's what I'm interested in. I'm also interested in the size of the structure, okay? Because if I want to access individual members of the structure, I need to know, how big the structure is in order to find out, where to find it on the stack and stuff like that. So what I'll do is not to find out what is var1, but I'm interested in finding out where is var1, not the value, but the address of var1. And I'm going to change the size of this terminal a little bit, just so the people in the back can also see the content. Okay, so it's telling me that the structure, var1 is at location 964 somewhere on the stack. Okay, all right, that's okay. How about the first member of var1, which is I? It is located at exactly the same place. Well, that's okay. Okay, it's something that seems to be fairly natural. Okay, because it's the first member of the structure, so it is at the same place where the structure itself begins. Okay, makes sense. Let's take a look at buffer. The address of buffer is 4 more than the address of I. Seems to make sense too. Okay, because from the compiler's perspective, if it is trying to be lazy as lazy as possible, rearranging things is not lazy. It takes extra effort. So if it just kind of say, okay, later members of the structure will have a higher address, that seems to make sense. And I is a 32-bit integer, which takes up 4 bytes, and that's why buffer is 4 bytes after I. Seems to make a lot of sense. Okay, and remember, buffer only has 27 characters. So now the question is, what is CH? And CH is located at location BFFF983. Okay, so is that making any sense?
Yeah.
Because these are all in hexadecimal. Okay. All right. So if I say print size of struct X, it is 32. Does that make sense? Makes perfect sense, right? Because the integer is 4 bytes, then we have a buffer of 27 characters, and then we have 1 single byte after that. 28 plus 4 is exactly 32. Okay, great. So that means if I want to access individual members of a structure passed to a subroutine written in assembly, I can just rely on these offsets, right? An offset of 0 to access I, an offset of 4 to access buffer, and an offset of 27 to access, 31 to access CH as a member. But the problem with that approach is, if I change the structure, if I insert any members or reorder the members, the assembly code will no longer be consistent with the C code, which kind of is not good, because it thinks it's still accessing the structure correctly, but it's actually not doing that. Okay, so what we'll do is we'll go ahead and look at this program again, but this time we'll restructure things a little bit. At least I'll pull out the structure definition into a header file, which is a very conventional way of doing things, because if I do have any other functions, other subroutines related to struct X, I want that to be shared. So the first thing I'll do is to take out the first 7 lines and create a x.h header file with the structure definition in it. And the more conventional way of doing things is you use a macro, x_h, to guard against multiple includes. So, not sure whether you guys have seen this kind of code before.
You have it defined.
Oh, okay. Not refined. So what this does is it is guarding against the multiple include of x.h in a file. Now, it doesn't make any sense if someone just have 2 pound include right next to each other and they all say pound include x.h, pound include x.h. That doesn't make sense at all. But sometimes when you have a pound include a header file, pound including another header file, it is inevitable that you can pound include the same file several times, when you are compiling a C program. And that's why we need something like this. It's basically to say, it's okay to reparse line 1, as many times as you want to. But if the macro x_h is already defined, then line 2 all the way up to line 10 will not be seen by the compiler anymore because it's inside a conditional statement as far as the preprocessor, the C preprocessor is concerned. Okay. But I will put the structure definition here. Then in the original code, which is struct.c, I'm just going to do a pound include x.h, basically to include the definition of struct x here. So, yep, go ahead.
What was the H for?
Oh, it's just saying that this is a macro, related to the pound including of a header file. That's basically what it is. Okay, so not really a whole lot has changed at this point. And then I might want to include another source file. Okay, so we'll go ahead and deal with multiple source files now. We'll go ahead and say init x as a source file. So this one is only there to initialize a struct x thing. So we'll say pound include x.h void init x. And what it needs is a pointer to a struct x. So we have a pointer here. And what this subroutine is going to do is to say, PTR points to I gets a value of 0. PTR points to buffer gets bracket 0 gets a 0. So it becomes an empty string. And PTR points to CH gets 0 as well. It's a null character all by itself. Not really, important stuff. Just stashing some code here to change whatever PTR or the pointer points to. Okay. So if I have something like this, I can go back to the original code. Actually, the first thing I want to do is go to x.h and include the prototype of init x in the header file, which is also a very conventional thing to do, is to include all the subroutines related to a particular structure into the same header file. Okay, so using this technique, any source file that is pound including x.h not only will know about the structure of x itself, but it will also have all the prototypes related to struct x. This type of programming is also known as abstract data type programming. It's something that predates object-oriented programming, but eventually leads to object-oriented programming. So if I get back into struct.c, which is the one that contains the main program, I can now kind of get rid of all of this stuff here and just say init x wherever var1 is. So I can now initialize var1 by calling init x. So this is the current structure of my program. I have main in one particular file, I have init x in the other file, because I'm setting it up so that I can implement one subroutine in C and the other one in assembly code. Are we kind of still doing okay so far with the source code? 2 source files that we have right now and 1 header file, and that is shared by the 2 source files. Is that okay? Okay. So we'll double check on this one. And at this point, I really need to use a makefile to do all this stuff here. So I'm going to cheat a little bit and look at my own makefile link here, which is something that we did last time. The homework also makes use of the makefile. And install make. There we go. More about the make program. And I'm just going to copy all of this, stash it into a single makefile. Has anyone looked into this makefile and tried to make sense out of it? Kind of? Okay. Okay, so cat to makefile, and just paste it from the buffer, clipboard. Customize this makefile. Okay, the cool thing about this makefile is it can basically deal with any type of source file. So right now we have struct.c and initx.c. So here we have struct. We don't have any C++ source file, so we'll just go ahead and delete this reference here. We don't have any source file in assembly yet, so we'll delete that as well. We want to call the executable main. That's fine. It doesn't have to be struct. This stuff is all kind of commented out, so we will delete all of that so it doesn't kind of interfere with what we are doing here. And I think that should be it. Okay. So we say make, it's missing separator. Oh, okay, we had the same problem before on line 14. Oh, it wants to replace this with a tab. Same thing here. This is one problem with copy and pasting from a web page, because the actual tab character is now missing. And I think we need the same thing here. Nope, a whole bunch of stuff here. All right. Target pattern contains no percent on line 15. Oh, same thing. I forgot to put a tab in front of all the lines. Fix the other one. Okay, init.d failed. Okay, recipe for target init dot. Okay, I make a mistake somewhere. Init x.c is here. Oh, I know why. Has to do with the backslash n. There's not, you cannot have anything trailing, the backslash n, which is a line continuation symbol. So if I have any characters after the backslash n, it's not going to work. All right, so I'm going to be lazy here. To do it. Okay, unknown command on line 14. So I can't see the unknown character.
Could be the single quote, using the wrong one.
This one? Oh, you're right. I'm not sure how many of you can actually see the difference between this one and the one that replaces it. It has to do with the HTML or whatever tool that I use to do the encoding. Oh, it's missing a whole bunch of stuff here too. Ah. Yep, it's definitely using the wrong one. But when I did the replacement, I actually kind of screwed up on that one too. Great. There might be a link on Moodle. Let me see if I can find it.
It was part of Find Max N, wasn't it?
Yeah, it is. I just kind of cheat a little bit and use my own notes. Oh, it's already in here. All right, so we'll go ahead and just copy it from. Okay. Struct.c, init x.c. There we go. All the pitfalls of copying and pasting from HTML into a file that is tab and quote sensitive. Very much so. Okay, so the program does compile and it does run too. There's nothing really interesting going on with initx. It's just an example. So now the question is, how do we get the assembly version to work in this case? So the first thing we need to do is to write a program called, you can call it anything you want, but it has one single purpose. It generates the code that will be included in the assembly version of the program. Okay, so I'm going to show you exactly what it looks like. Let's call that struct x include generator.c. Okay, that's good enough. Okay, so it's going to include a pound. It's going to pound include the same header file, so that we have the definition of struct x. But inside here, the other thing it has to include is stdio.h, so that we can have printfs. And then what we'll do is we'll have struct x, just var1. Okay, it doesn't matter how you name the variable. And what we'll do is we'll have a whole bunch of printf statements. The first one is going to be x underscore size, okay, and equal to %d, which means I want to print something in base 10 in a line v character. And %d in this case is just size of var1, or struct x would also work in this case. Printf x underscore I, which is the displacement to member I, and that displacement can be calculated using this little equation here. And I think can cast anything to a void pointer, so I can cast var1.i into a void pointer, and then subtract the void pointer casted again from var1 just var1 itself. And then from here, we'll just go ahead and do it 3 times for buffer and also for ch. Could have written a little macro to do this because I'm repeating kind of the same structure of the code all over again. Okay. And let's compile this first, make sure it runs, and then I'll come back and explain what it does.
Get typos.
Oh.
You copy, paste the typos.
Oh. We'll let the compiler figure it out. Okay. Undefined reference to printf. Okay, I see what you mean. Pritnf to printf fixed. We compile, and if I run this program, it doesn't seem to do anything particularly interesting, because all it does is to say x underscore size is 32, x underscore I is 0, which means 0, member I is 0 bytes away from the beginning of a struct x. That's basically what that label means. X underscore buffer is 4, which means member buffer is 4 bytes away from the beginning of a struct x, and so on. Okay, so at this point, this program is going to be sensitive to the definition of struct x, and I can change my make file to take care of this one too. So in the make file, I can say include generation executable is struct x include generation. That's the name of that particular executable, and then we have to have a rule. I think that it will do by itself. Let's see. Make struct x include gen. It's up to date. Okay, let's get rid of it first. And it knows how to generate it, but if I update the header file, it does not automatically update because it doesn't have the .d file or the dependency file generated corresponding to this one. This one is a little bit tricky. Let me go back to the make file first. Okay, this one is a little bit tricky because we have to have a way to trigger the recompilation of a struct X include generator whenever the header file x_x.h is updated. So essentially, what we need to do is we cannot add it here either. Okay, if we add it here, then there will be two main in the executable because all of this is corresponding to main itself. So this one kind of needs its own rule, to generate, the header file or the dependency file. Let's see here. I think the original, the one that I copied from actually has an engine to do this already. Maybe not. Okay, so does everybody kind of understand what I'm trying to do here? I'm trying to trigger the recompiling of include gen executable whenever x.h is updated, but I don't want to have to manually state that dependency. I want the compiler to be able to figure it out by itself. I think I know what to do with this. Okay, so I need two specification of source files. So the other one is going to be include file generator execute C file, and I'll put struct x include gen here and .c. This is the source file. And I will replicate the rules down here to include that. It's called include generation C file. So that would also include the, it will automatically make the .d file for this executable.
Don't you need to include the clean to delete the...
So it will clean that up too? Sure. That will take care of the .o file. And that will take care of the dependency file. Okay, so you can see how it is generating the dependency file. If you want to take a look at the dependency file, this is what it looks like, which is basically just saying that include struct x include generator.o, which is the object file, depends on both the .c file and also x.h. But that is done automatically by the makefile itself. If I pound include another include file, the dependency will be figured out automatically. I don't have to do anything manually. Okay, so what we want to do is to give you, I'll just give you one sample program to do this, just a shell of it. So what I want to do is to implement initx in assembly code. So this is what I want to do. And I want to do a pound include here and say I want to include x.inc, which is the include file itself, and all it's going to do is to do a .global initx here, and all for the time being I just wanted to return just like that. Okay, I'm going to update the makefile and say that I don't use the .c version of this anymore, and instead I'm going to refer to the assembly code version of this, which is initx.uppercase-s. So this is how I shift from the C version to the assembly version. And then we have to this will Okay, I have to indicate what is the name of the include file, because otherwise it doesn't know what it's called. So we'll call this one x.inc for the include file for struct x. And we'll make clean, make again. It's still using the .c version because it has priority over the assembly version. So we'll have to rename the .c version to initx.c.back, make clean again, and then make. Okay. It's not finding initx.c. Recipe for target init x.d failed because x.inc does not exist yet. It's not figuring out this particular dependency. It doesn't know that x.inc depends on the struct x include dot generation. That dependency is not it's not figured out yet. Now it does it. So we have to give it a seed so that the file exists in the first place. Okay, so I have everything done at this point. If I change x.h, which is the C version of this, and I switch these things around a little bit like that, and I say make again, you can see that it will go through several things. Struct.c is recompiled obviously because x.h is updated. Okay, I have an updated structure definition. But you can also see that it's automatically recompiling and relinking the include file generator. And once that one is updated, it would also regenerate x.include, which is also used in the compiling or the assembling of init x.s. So if you take a look at x.inc, the displacements have now changed because I just reordered the members a little bit, and you can also see the size has changed as well. It was 32 before. Do you guys remember? Struct x used to have a size of 32, but by reordering the members of the structure, it is now 36. Because it wants members to, it wants 4-byte members to be at a 4-byte boundary, and that's why it wants to line things up in a slightly different way this time. Okay, so this is how we're going to set things up for Thursday. Basically, we want to have one makefile system that can take care of structure definitions in C and automatically update and include file that is used by the assembly version of the same program. So that this way, if you change the C code, the structure definition, it will automatically make sure that your assembly code will be compiled in a way that is compatible with the C code. So we'll continue to work on this program. We'll finish initx.uppercase S on Thursday. Don't forget, we do have the homework assignment due on Thursday. If you're not done yet, I'll be in the lab, so it will be helpful to do it in the lab.
Test on Thursday.